Will be today and tomorrow. Then it's Friday. There will be question session, so I'm here to discuss the project. If you want to meet, and next lectures are next week, Tuesday and Friday. So,
yeah, should work, right? Yeah. Okay. Thanks, Stefan. And yeah, I'm really happy to give this lecture on Bayesian networks, or 4 lectures actually. And as Stefan said, on Bayesian networks in the course of knowledge representation. And most of the content and slides are taken from Arman Achar, which did the course the past few years. Let me say some things about me. So, well, as Stefan said, I'm a PhD student here at the FU now since a bit more than a year. And my research interests are more on reinforcement learning and causality. And because of causality, I also work with Bayesian networks actually a lot, which was a nice fit for this lecture then. From background-wise, I did my bachelor in cognitive science in Tübingen in Germany, and my AI here, where you're sitting, basically. Yeah, if you have any questions, feel free to write me an email anytime, or on Slack is even easier, but you can also just drop by. I'm on the 10th floor in the eastern side of the A wing, and just in a random room you will find me. Just feel free to drop by anytime. What are we going to do in these 4 lectures? So in today's lectures, it's more introductory and some basic concepts about beliefs and probabilities. Then next week, or well, tomorrow actually, I will go into the definition of Bayesian networks and some first things that we can do with them, and talk about graphs that will be very relevant for Bayesian networks and what independencies they entail. In the 3rd lectures, I will give you some tools that we will need to do some reasoning and some inference on Bayesian networks. So there will be a lot of algorithms that are useful for these kind of things. And in the last lecture, I will show you how to reason over these Bayesian networks finally. So the most interesting part, how can we do this with these tools that we've learned, and what interesting questions we can ask. What we will not address in these lectures is how to do approximate inference. So we will really have hard algorithms that give you the exact answer of a question that we have on Bayesian networks. And we will also not talk about how we are learning these Bayesian networks. So in this course, we will assume we're giving these Bayesian networks, and how can we find information in these Bayesian networks, and what kind of information. And so let's start, I would say. Are there any questions so far? All right, so I already gave the overview away a bit. First, I will introduce what a belief is and motivate why will we need Bayesian networks. Then I will talk a bit about how belief can change when we get evidence. And so what independence is. So most of this stuff probably you already know, but I want to take everyone on the same page, and so that we talk about the same things. And then I'll introduce some more notations of belief and of probability that will be useful later for Bayesian networks, like marginalization and the chain rule and these kind of things. So hopefully you're already familiar with some of these things, and let's get away with first a bit of a motivation. What do Bayesian networks do? What are we trying to solve with it? The idea is that in our world, we have so many things where we have really uncertain knowledge. So we are not really 100% sure it's true or false, for example. And we want to find a way of modeling this knowledge. And such applications are decision making or spam filtering, a lot also in natural language processing, where I might get a distribution over next words, for example. And in general, having a way of reasoning over uncertain knowledge is super important in AI. And this is useful also if we can represent it, we can also reason about it. So we can ask interesting questions about about uncertain knowledge, and reason and inference of it. And this is exactly what we're trying to do with Bayesian networks. So we're trying to model knowledge that is uncertain and model it in a way that it is fast to reason about and that we can actually reason about. Of course, there are some more models that model uncertain knowledge, of course, but Bayesian networks is one of the really big ones that is used everywhere in some way. So beliefs, what are we going to talk about? Beliefs. Let's first of all think about a scenario that we will drag throughout these 4 lectures, in which we have the possibility of an earthquake happening. So we have some information, earthquake is happening or not, and we will be talking only about Boolean variables. So really just 2 cases of the variables. And of course, all of this can be extended to more values or even continuous space. But in this course, we will really talk about Boolean variables. And our scenario is that there can either be an earthquake or not. We can have that a burglary is happening or not at that moment. Then there can be a radio report of an earthquake and an alarm. So basically you can think we hear an alarm somewhere, right? And the last thing is that someone could be calling the emergency line or not. And this is the scenario we're gonna drag over these lectures. And let me start with some definitions. When we talk about a world, and probably this is also in the first part of the whole course already covered, but then we want to talk about instantiation of all the possible variables. So in our case, a world would be earthquake is happening, the radio is reporting about it, no burglary is happening, we hear an alarm, and someone is calling the emergency line, right? This would be one world. And we have already, as also in SAT solving, we have this kind of representation where we then can say, okay, this is true or false, right? The scenario that I just described can be true, but it can be false. And we want to go beyond this and say, I have some belief in this happening, right? So some value that is between 0 and 1, a probability also, as you know it. And this is what we're gonna look at. We're gonna look at the degree of belief or the probability of worlds. So how much do we think is this true between 0 and 1? And yeah, we will call it degree of belief or a probability. And already first nice formula, but it's really straightforward. We have all these worlds, right? As I just described, which is an assignment of all the variables. And now we want, for example, the probability of that an alarm is ringing at any given time. And what we can just do, we have a definition of the probability of each world. So all of these scenarios already have a certain belief up front. This is where I said we're not going to learn the Bayesian networks. We're going to be given the information up front. So we know what the probability of a world is. And then if we want the probability of a certain event, for example, that alarm is ringing, then we can just sum up the probability of all the worlds in which the alarm is ringing. So far, so good, hopefully, but please also feel free to just interrupt me for questions anytime. I don't mind it at all, so you don't have to wait. Yes. Yes. So the question is, what exactly is an event? An event can be any assignment of the variables of a world, right? An event could, for example, be the earthquake is happening and the alarm is ringing, or just the earthquake is happening. Right? I'll maybe go directly to the example where you will see it. Yeah.
Just a question: how do you know that what prevents the probabilities from summing over 1? Isn't the number of worlds somehow relevant in that equation?
Yes. So what will prevent the probabilities of going over 1? This is the knowledge that we learn, right? We define it in a way that they will not be over 1, even if we sum them up. So what is event, what is world? Let me just go right into example. So we have here a smaller version of our scenario where we just have an earthquake is happening, a burglary is happening, and the alarm is ringing. And in each line, you see, does this have a point? In each line, okay, which you cannot see in the slide. Good. on each line you see one world. So you see one assignment in world 1, an earthquake is happening and a burglary is happening and the alarm is ringing. And this world has a probability of 0.019. Okay. And what we want to know now is, let's say we want to know what is the probability of an earthquake happening. And what we do, according to the formula before, is we look at all the worlds in which an earthquake is happening, and we sum up their probabilities. This would be world 1, world 2, world 3, and world 4. And the earthquake would be the event, coming back to the question from before, and the world would really be an assignment over all the variables. Yeah, and we'll see a bit more complex events later, where we not just have one variable. Next example, what would be, maybe someone can say, the probability of burglary happening?
World 1, 2, 5, 6. Add it up.
Yeah, exactly. The probabilities of these worlds added up, right, which is 0.2. And right, not burglary then, the other worlds summed up. And we'll go more into this property later. And what is the probability of alarm happening? Let's do a last one. You don't have to give me the exact number.
1, 3, 5, 7.
Yeah.
Exactly.
Right. So is it clear now what the event is and what the world is? Yeah. Okay, so we defined some beliefs now, what it is, probabilities, belief. I will use the two terms interchangeably. And we want to look at some properties, which should also not be very surprising to you. First of all, because they're defined like this, we have that every belief must be between 0 and 1. All right. For any event. This answers your question. So this is just the properties that we constrain on it. And the next property is, what do we have if an event is impossible? So this event cannot happen. Let's say an earthquake is happening and an earthquake is not happening. Well, then the probability should be 0. And on the opposite side, for valid events, we have that the probability should be 1, right? It's always true. And the next one we already quickly saw. Is there a question? What about the probabilities for Boolean variables about an event and the opposite of the event? Well, they should sum up to 1. We saw this with the burglary example before. The probability of a burglary happening plus the probability of a burglary not happening is 1. This is really just the basic properties of belief and probability. And the last one, we won't need that one so much, but if I have the probability of either of two events, then it's just the probability of each of the events minus the probability that they both happen at the same time. And why minus this probability? Well, this probability is already counted in the probabilities of alpha and beta. So in each of them, so if we sum them together, it would be twice. So we have to take one away. One example about this fourth rule that we already saw with the burglary, because it has a bit of a special name that we will refer to later also, is partitioned worlds. And it basically says we have our worlds and we can divide them into sets that together are again the whole set of worlds, right? So basically this rule, right? Alpha and not alpha cover all the worlds, and together they should have a probability of 1. More formally, right? We call it partition if we have both all the worlds that entail alpha and all the worlds that entail not alpha, and then alpha, then they are partitioned into these two events. So how is this useful? We saw this already, the probability of earthquake, and it's just the sum over those. And without taking the sum again, because of this property, we know what the probability of not earthquake is. 0.9, right? Because of the property that both of them have to sum up to 1. And we know the 1, so we also know the other one. Is this clear?
For the concept of partition. So it's either A or not A. So these are two partitions in that sense. But one.
Yes. So the two events, alpha and not alpha, basically cover all the possible worlds. But there is no overlap between the worlds that entail alpha and the worlds that entail not alpha.
This is one partition or two partitions?
The partition is both of them, right? So you have the set of worlds, and you split them into two partitions. Then, so far we have seen that we can have these state of belief or probabilities that we're given up front that tells us how probable some worlds are, and we also know how to calculate the probability of one event from that. And this is from our prior knowledge. But what happens now if I'm already hearing an alarm, for example? Then somehow we have the problem that it changed the probability table, right? And just for some terminology, we call this, okay, we're hearing the alarm is happening in evidence. And we call all the worlds in which this event is happening consistent, right? A world in which an alarm is not happening, but I hear an alarm is not consistent, not a consistent world. And what we need to do now, so we hear an alarm, right? But our probability table tells us the probability of an alarm happening is this number. But this cannot be, because we know that it's happening. So the probability of an alarm happening must be 1. And this is what the table shows us. And we have to therefore update this probability table somehow, given we have an evidence. And we write it like this. So we have a conditioned probability with this bar, right? Whatever comes in the first part, the probability of whatever comes in the first part, given alpha, which could be the alarm is ringing. And we want to update it. And we call this conditioned table or distribution, in the extended case, a conditional probability table. And the question is now, how, given that we have an evidence, how can we update our state of belief? And there are two cases. One of them is the inconsistent worlds. So the worlds in which the event that we are observing is not happening. And well, it's pretty straightforward, right? I said it before, the probability of an alarm ringing, giving an alarm ringing, well, should be 1, although our table says something else. But on the other hand, that means that the probability, because we have these partitioned worlds, the probability of an alarm not ringing, given I hear the alarm ringing, well, must be 0, right? So that every world in which the opposite of our evidence is happening is inconsistent, and it needs to be updated to have a probability of 0. So we know how to deal with the worlds that are inconsistent with our evidence. This is the first update we can make on these worlds. Any questions? All right. Now the bit more interesting part, because this is pretty clear. What do we do with the worlds that are actually consistent with our evidence? So that in all these worlds that say that alarm is true. And we can use some properties of belief and some desires basically as constraints and how we want to update it. And our first constraint is, well, all these, the probability of all the worlds given this alpha must sum up to 1, right? This is the basic definition from probability, they must sum up to 1. So this is the first constraint that we have. The second constraint is a world that is impossible, right? So it had 0, probability of 0 in the beginning. Well, if we observe an evidence, it should still remain impossible, because otherwise it wouldn't have been impossible from the start. So this is our second constraint. For impossible worlds, we assign probability of 0. And be careful, impossible here is different from inconsistent, right? The impossible worlds could be consistent, as insofar, okay, they say something about alarm being true, but it could still be impossible because of some other configuration of the world. And as a last constraint, we want to say that whenever we have a ratio of probabilities before the evidence, this ratio should stay the same when we have the evidence. It's just an additional constraint we make. So now we have these constraints, but how do we actually update now for consistent worlds the belief state? And actually not so hard. And maybe you've already seen this formula, but now I introduce it a bit more from where it's coming from, right? So the probability of any given world, given our evidence, is just the ratio of the probability of the world that we had before the evidence divided by the probability of the event.
Last point, last slide, how does the ratio remain same?
So this is just a constraint we make, right? This is, we say basically, this is how we want it to be.
So why do we want the ratios to be same? Like if the word is different means.
Because the evidence should not change anything about, for example, one world being twice as possible as the other one. So if you have, or let's take two worlds that have equal probability, right? Knowing one of the, well, knowing an evidence should still leave them with the equal probability. Because this has also nicer properties later when we want to update and calculate with these kind of things. More maybe follow up or yes? Okay. All right, so we had these constraints, and this update is basically an option that we have for updating our beliefs, where we just scale the original probability by the probability of the event happening. And yeah, in other words, you could say we normalize the belief with respect to alpha. We could, I will probably use this terminology. And we have now the case for inconsistent worlds, right? Where we say we should just stay 0. And we have the update for consistent worlds. And remember that this update also includes the impossible worlds, right? They will, if you see in this formula, if the original probability of the world was 0, it will just stay 0. Right? We can say that the update given an evidence is just these two cases for inconsistent and consistent worlds. Yeah.
Be the numerator probability of omega intersection alpha. So that's the basic definition of condition probability.
It should be equivalent then, but you have to be careful with the inconsistent worlds, right? And you will see that this update, you can switch it around. We'll look at the base theorem also. Yeah. So yeah, indeed. Well, although this would be then for two events, right? Because omega here also contains alpha, the variable that alpha assigns. So then what you're describing is for two events, like one event conditioned on the other. Here we have a world conditioned on an event.
Omega intersection alpha is much smaller than omega.
Omega intersection alpha is just alpha.
Right?
Yeah.
Yes. Okay.
Yeah. Okay, let's maybe look at an example. We have our original table with the earthquake, the burglary, and the alarm, and our original probabilities that were given to us. And we observe now, okay, an alarm is ringing. So this changes my whole belief in the whole worlds with this update, right? You see that all the rows where alarm is false are just 0, and all the other rows are just divided by the probability that alarm had in the first case. Yeah.
What is the dot represent here? Just
Alpha, or I didn't hear it, sorry.
what is the dot?
It means over all variables. So it would be dot would here be earthquake, burglary, and alarm. Just so it's shorter.
So it's meaning like the update one.
No, the dot one, the updated is also always with the conditional. So it's the last column. The one with the dot just means over all these variables. So instead of the dot, you can really just write earthquake, burglary, alarm. And what does it mean? So we have these original probabilities that we already saw before for an event. Remember, this is just the sum over all the worlds that entail this event. And we can see how they change. So let's look at the probability of burglary given an alarm. What would we expect? Well, if I hear an alarm, it should go up, right? It's more likely that a burglary is happening. And the same goes for earthquake. And this is what we actually also see when updating the table like this. So we see that if we observe an alarm, if we hear an alarm, then it's more likely that the burglary is happening. Okay, so one first rule. And this ties to your question from before, that about the probability of a world given an event. Right now, in most cases, we're more interested in the probability of an event given another event. And this is done with Bayes conditioning. So whenever we have 2 events, alpha and beta, and by the way, an event could also be that burglary is happening and earthquake is not, right? It doesn't have always to be one variable. We can just express it as this. This is what you said, right? And this indeed, you can derive it by just going through summing over all the worlds and replacing what does it mean if it entails both. And then you just end up with this expression for 2 events, right? Before we were talking about a world conditioned on an event, and now we're talking about an event conditioned on an event. Well, it's a fraction, right? So of course, this is only defined if the probability of beta is not 0. Which makes sense, right? If I know that an earthquake can just not happen, and I observe an earthquake, then something is wrong with my belief state. All right, more examples. We have this scenario where we have as evidence. This time we don't hear an alarm, but we hear the earthquake. And we know from the table before that the probability of burglary is 20%. And now we do this update with our evidence, and we observe that the probability of burglary just stays 20%. So nothing changed, although we know that an earthquake is happening. But if we look at the probability of alarm, and we observe an earthquake is happening, it goes up. Right? So this is, we go in more detail a bit later, but it's already some information about somehow earthquake doesn't really give any information about burglary. So some kind of independence. The second scenario, we can look at burglary, the evidence that we know that a burglary is happening, right? And again, if this is happening, our belief in an alarm goes up, but our belief in an earthquake does not go up, right? So we see it goes both ways for burglary and earthquake. They don't change when we know the one from the other. 2 more examples. in this scenario, we know that alarm is true. So this is already a given, right? And now we say we hear an alarm and an earthquake is happening. So let's look at the probability, at the first probability, where we say, okay, how likely is it that a burglary is happening given we hear an alarm? And this we obtain again just from the updated probability table on the alarm. And in the example before, we said that observing an earthquake does not influence our belief in a burglary, right? But now we don't only observe an earthquake, but we also observe alarm, and suddenly the earthquake does influence the probability of burglary. Intuitively, you can explain this, right? It goes down in this case, that, okay, so an alarm is ringing, and we want to know what is the likelihood of a probability, right? And we know that also an earthquake is triggering an alarm. But now we know that the earthquake is happening, so we have a very good explanation of why the alarm is ringing. So our belief in a burglary goes down. We believe less that the burglary is the cause of the alarm. Similar example, right? Again, we hear the alarm, and this time we do it the other way around. We calculate the probability of a burglary given an alarm, and now we also know for sure it's an evidence that no earthquake is happening. And then it works the opposite way, as I just explained, because then the reason for the burglary being the cause of the alarm must increase a lot, because the earthquake cannot be the cause. We know that there is no earthquake. And yeah, the nice thing with all these probability tables and the updates of belief is that with this simple update rule, we can already cover a lot of knowledge and a lot of dynamics about our system. Because we basically had one update rule and one rule how to compute the probability of an event, right? And with this, we can already see a lot of reasoning over and there's no Bayesian networks yet involved, right? We just have a probability table. And this is also why we chose the update rule as it is with this fraction, and that the ratio stays the same, because otherwise these properties would maybe not hold. Is there any questions so far? Okay. Now, in the last 2 slides, I already showed that some events seem to have no influence on each other in some way, right? One does not really influence the belief in another. And then again, in some cases, when we have additional information, the same events might influence each other. And this is, and you probably know this notion, more formalized in independence, right? This is what we saw before. The burglary is the same probability whether we observe an earthquake or we observe no earthquake, or we don't observe an earthquake or anything. It just stays the same. And we want to give this property a name, and we call it independence. And one of the 2 definitions of independence, by the way, notice this sign that we will be using. It will be everywhere, right? These 2 lines with the horizontal line, which we will just use for independence. And so the 2 events we say are independent if the conditional probability is the same as the unconditional probability. We see it in the first line, right? We want to call this behavior, that burglary doesn't change whether we know about earthquake or not, independence. And this is exactly what this formula says. So for any 2 events, alpha and beta, we call them independent if the conditional probability of alpha given beta is just the probability of alpha. Okay, and we can also formulate this alternatively with the base conditioning that we saw for 2 events before, right? where we said the probability of the condition 2 is just the intersection of the two events, the probability of the intersection times the condition variable, divided by the condition variable. And then we get to this result. Yeah, maybe I can see, I don't know if you can see my pointer. Right, so this is two equivalent statements about independence. And you can easily see it by taking in the first green line, the probability of alpha given beta. We saw in base conditioning is just this fraction of the probability of alpha and beta divided by the probability of beta, right? So if you just plug that in and multiply the probability of beta to the other side, you get to the second result, right? It's just one step. And whenever it's useful, we will be using one or the other. And both of them mean that they are independent. Okay. So we have two independent variables or events now. And we saw already before that it can change whether they are independent or not, given new information. So it's a dynamic notion, this notion of independence, considering we have evidence. Basically, it says if we have independent events, they can actually become dependent when we have new evidence. And we don't know really upfront which evidence that is, right? So we don't know which will make it independent or not yet, at least from the table alone not, but in Bayesian networks we will see it's actually not so hard. And this is just, again, the example that we had, right? That burglary is independent from earthquake. And we also saw before already that the probability of a burglary given an alarm, it should be higher, but yeah, don't mind the exact numbers, right? Is 0.74. So we observe an alarm that makes the probability of a burglary higher, right? And we know that burglary and earthquake are independent, but now given alarm, suddenly it matters whether we observe an earthquake or not. So conditioning on alarm makes the two variables actually dependent. And in this case, we say that burglary is independent of earthquake, conditioned on alarm. And this is the terminology that we use. So that independence we see can change depending on what evidence we have. No questions? Have you lost me completely or? So a more formal definition of conditional independence. Same as before, right? We want some formulation to work with. When we say that two variables alpha and beta are conditionally independent, right? So they are only dependent if we condition on another variable, if you want, if this holds, right? So, or they are independent, sorry, I said it wrong. Two variables are independent even if we have additional knowledge, if this is the case, right? So if I have alarm and earthquake as an evidence, and the burglary would be independent conditionally on earthquake in this case, then I would be able to just ignore earthquake, which in our case is not true, right? So in our example, we could see that they're not conditionally dependent. And we can also get to the next result. We have two just equivalent formulations again, that the probability of two events happening conditioned on another one is just the separate probability, of course, only if these two events are conditionally independent. And again, we will just use any of these two formulations dependent on what is more useful for us. I'm planning to make a break, but maybe you have questions about any of what I just said. There's enough time. I shouldn't have said the break thing then, I guess. But yeah, feel free to approach me also in the break. We'll have 15 minutes. All right. Good. So we've seen now in the first part, we've introduced all the terminology we need about worlds and events and beliefs. And then we saw how we can update beliefs given some evidence. We know what evidence means now. We know what a conditional probability is. And then we also looked into independences and conditional independences. And we already saw some very basic properties of belief and probability, like these partitioned worlds, and that the probabilities need to sum up to 1. And now in this last part, we're gonna see some more properties that are gonna be very useful later when we're actually dealing with Bayesian networks. And we'll also go through a bit more extended example of the Bayes theorem. And yeah, so I got this question about why am I not showing anything with graphs yet? Right? The reason is that all of what we're doing, we don't need a graph, right? And then for Bayesian networks is where we take the advantage of the graphs. So everything we did now is really just from this initial table that we got. We can do it with that. Are there, after this break now, any questions to what you heard so far? No? All right, so as I said, we'll see some more properties of belief or probability. The first, and this is a really, really central one, is the chain rule. That will allow us then in Bayesian networks to compute a joint probability from conditional probabilities, right? And it's based on the Bayes conditioning that we saw before. And I just said we want then to compute the joint probability from conditional probabilities. Maybe I should say first what is a joint probability, right? So if you have some events, then the joint probability of these events is that all of them are happening. And if I talk about, so an event we know is an assignment of a variable, right? But if I talk about the probability over the variables, so over all their assignments, then it's also a joint probability table. And we saw in Bayes conditioning that we can calculate the conditional probability out of this fraction, right? On the other hand, this means equally that we can calculate the joint probability from the conditional and the prior probability, right? So if the probability of 2 events happening at the same time is the probability of the one condition on the other times the probability of the conditioning variable. This is what we saw before. It's just the rule that we saw before. And what the chain rule now does is extend this result a bit to like an arbitrary number of events, where we say that we can calculate the joint probability of events. So this would just be all the possible events, for example, by taking step by step the probability of the first event given all the other events, right? And then the probability of the second event given the remaining events. So you can imagine with a lot of events, this gets a very long expression. But this is how we can recover the joint probability from conditional probabilities. And this will be very important later because we will always want, or in many, many cases, when we reason in Bayesian networks, we want to talk about joint probability distributions, which we can calculate like this. And we can then, when we look at independences, even simplify all of this. And if we can calculate the probability of joint events, we can also calculate it for every case. So let's say each event is the assignment of one variable in our world. So we had burglary. Let's say alpha 1 is burglary, alpha 2 is earthquake, and so on, right? Then we can calculate the probability of all worlds like this. would be an example. Just by taking these conditional probabilities. And as I said, this will be very important for Bayesian networks. So this is the chain rule. It's really just an extension of the base conditioning that we saw before for multiple events. I will also, the question came, I will share the slides after, of course. Then in partitioned world, we already implicitly used these properties of disjointness and exhaustiveness. So this has is not necessarily specific to Bayesian networks or anything. This is just two terms that we will need later. So I'm introducing them. And we're looking at a set of events, our betas, and we will call them disjoint or mutually exclusive if they all represent a distinct part of the worlds. So we had in the introductory example alarm and not alarm. They would be disjoint because all the worlds that entail either alarm or not alarm, and you take the sets of those, they don't have an intersection, right? So there is no world that explains both, so to say. And this means that they're, we also say mutually exclusive or logically disjoint, right? So the worlds that entail alarm is a different set with no intersection with the worlds that entail not alarm. And this is just what we will call exclusive events. And this, for other applications, also extends to multiple assignments of the variable. But we'll look at binary variables, right? So it's just not and true. And exhaustive is when we have a set of events, and the worlds that explain this sum up to all the worlds that are there, to the whole space, right? So if we sum up all the worlds that entail the events, then we end up with the whole space of worlds. So with the whole, we had 8 worlds, right? This also goes for the example of alarm and not alarm. If we take the union of all the worlds that entail alarm and the union of all the worlds that entail not alarm, then we have then alarm and not alarm is exhaustive, the set of these events. And we will often be looking at exhaustive and mutually exclusive events. So here, just that they sum up to the whole space is the exhaustiveness is not constricted to that there is no overlap in worlds, right? And we typically want to have both properties. So really just to, yeah.
Sorry, what does mods mean?
These are the set of worlds. Yeah, good question. The set of worlds that model beta, that entail beta. So the union of all the sets of worlds that entail any of the events should be the whole space of worlds. All right. And why do we need this? For the next nice thing we want to do with beliefs, which is marginalizing, or what you can also call the law of total probability. That basically tells you if you have events that are disjoint and exhaustive. So each of them models different worlds, but also taken together they model all of the worlds. Then you can make some kind of case analysis. Then you can compute the probability of an event by, so let's say we have a list of betas, a set of betas that are disjoint and exhaustive. And we also have an alpha, right? And we can then calculate the probability of alpha by just summing up the probabilities of alpha and beta 1, alpha and beta 2, alpha and beta 3, if these are disjoint and exhaustive, right? And this is basically what we state with marginalization or law of total probability. That we just, so this is the first expression, right? The probability of an alarm would be the probability of an alarm and the other events, for example, earthquake and not earthquake, summed together. And this, the second part is again just using Bayes conditioning to express it in a different way. It just states the same thing. Do you see how the probability of alpha and beta I is the same as the other one? We had this before, right? Bayes condition. I'll put it on the blackboard so it's always there. We had it's just how we did between the two things. Yeah. So this is the law of total probability. Let's take some example. So here we assume that beta and not beta are disjoint and exhaustive. And then we can compute alpha like this. We don't have to go over all the worlds that model alpha. And this is just exactly equivalent writing it down with the second option. Just maybe, why would I write it like the one or the other? Maybe the only information I have are these conditional probabilities. And then I want to use that formulation. This only holds, as I said, because beta and not beta are mutually exclusive and exhaustive. Otherwise, this doesn't work. And yeah, this, why don't I want to just compute alpha in general, right, right away? Well, because maybe the special case, we have more information, right? We have, for example, the information about all the world, the probability of that, but we might not have the information of just earthquake. So this is also what we did before. We calculated the probability of earthquake by summing up all the other set of events that were mutually exclusive and exhaustive.
Alpha and beta are mutually exclusive. Did I get that correctly?
No, only the betas are mutually exclusive.
Beta and they're not beta.
Yes.
That goes by definition, right?
Sorry?
This goes by definition.
In binary case, yes. Yeah. So yeah, because we know we have binary variables, beta and not beta are mutually exclusive. All right. And Bayes theorem always sounds a bit scary. It's just what we saw a bit more in detail. So we're working a lot with these conditional probabilities, right? We say, okay, alarm given some, I don't know, given an earthquake is happening. And now in calculating this, we might need these probabilities, but sometimes we have only given the opposite. So let's say we have the probability of alarm given earthquake, but what we actually need to calculate our joint distribution is the probability of earthquake given we hear an alarm. And Bayes theorem basically tells us how to compute the one from the other. And you can see that, let's take a medical example, that we have the belief in a diagnosis given a symptom. We want to know this, right? This would be the probability of alpha and beta. So alpha would be the diagnosis and beta would be the symptom. And this might be information that is a bit hard to get. So what we want to use instead is the probability of the symptom given the diagnosis, right? Which might have more data on this. This might be easier to infer. And Bayes theorem gives us that. Basically, how can I compute the one from the other? By doing this. Yeah, and this, again, if you look at this formula, and you look at this, it becomes pretty clear why this is true. So this, right, also says that probability of alpha given beta is the alpha and beta, sorry, is the probability of alpha given beta times the probability of beta, right? We saw this now a lot of times. Well, but if I just put this here, right? This is also this, and I just get to the base theorem, and it allows us to compute the one from the other. Is it right? Yeah.
You need to reverse the.
The what?
Should be beta and alpha.
Beta given alpha.
Ah, right. This is why. This you mean, right?
No.
You need to replace beta and alpha on the other side of the equation. The other side of the equation.
Given alpha times probability of alpha.
Intersection is
Of wait here.
Yeah.
Yeah.
Yes. Yeah, otherwise it's the same with the one on top.
As in,
Right. Yeah. Okay. Of course, this was the whole point, right? Okay. Thanks. Thanks. Yes. Okay. Thanks. So this is the whole point. Yeah. So we can actually, this is nice because I have also a bit more example about this, and I wasn't sure if we can make it, but we can definitely make it. So let's go to this. An example about the Bayes theorem. So we have this medical scenario, right? Maybe you can all read a bit, or I can read it out loud. So we have a patient, and the patient was tested for a disease, and the test for this disease came out positive. And upfront, independent from the patient, we know that 1 in 1,000 people has this disease. And we also know that the test doesn't always give us the right answer. So it has a false positive rate of 2%. So it says it's positive when actually there is no disease, and a false negative rate of 5%. So it says the disease is not there, although the disease is actually there. And we want to know now what is our belief in that the patient has this disease, knowing that the test came out positive. Take a second to parse this. Okay, and we will talk about disease. We will use the variable capital D, and the outcome of the test will be the variable capital T. And yeah, we will only have these two. This basically summarizes what we just read, right? So our probability of the disease, this is what we know up front, is 1 out of 1,000 people has this disease. And the probability that there's so the false positive rate, which means the probability of someone not having the disease and the test comes out positive, is 2%, which means, just by rules of probability, right? 1 minus that probability means that the probability that the test comes out negative when the disease is not present is 89%. And we do the same with the false negative rate, which says, okay, the probability that the test is negative given the disease is 5%, and therefore the probability that the test comes out positive given there is a disease is 95%. So this is just put into mathematical terms of what we just read before. And what we want to find out now from this data is the probability that the patient has the disease given that the test comes out positive. So it's not given, right? And we can now just use the Bayes rule, right? Because what we want to find out is given T. This is what we want to find out. And the Bayes rule tells us that we can just take the probability of T given D times the probability of the disease. This is what we did here. Divided by the probability of the disease. Yes. A T. Again, of course. So the probability that we have a positive test. And the information we are missing is, well, this we want to compute, right? But also we don't have this. We don't have the probability of T. But we can compute it with the law of total probability. Because having the disease and not having the disease is mutually exclusive and also exhaustive. Right? So what we can say is that the probability of T by marginalization is the probability of T. So the test comes out positive given there is a disease times the probability of there being a disease plus the opposite case, the probability of having a positive test result given there is no disease times the probability there is no disease. And this was the law of total probability. This, you can see how it can already be useful because we don't have this kind of summarized information about the test, but we have these special cases that we know. And let me get the numbers. So this would just be 95% times 0.1%, right? And this is 2% times, what would it be? 9 times 99.9%. Yeah, is it clear so far? And the magic number is? Maybe someone can calculate how many percent that is. No. So this is our probability of the test coming out true in general, independent from whether we have a disease or not. That's kind of a summary of the data. Is it clear how we got this number? Right, all the information we need, we got in the. Right, so now we have this number, and we can plug it in here. Right. So what we get, and now I run out of space, is this was 95%. Times 0.1%. And is divided by, well, this equal. And you can calculate this, should be around 4.5%. This would then Is it clear? And we could also use the other notation for a solution that we had with this belief state, right? Where we know the probabilities for all the worlds, which are given like this. Right, so this is basically the lower part is just translated what is in the upper part. And we can then just, okay, this part. Yeah, and we know all these values, right? And we update it. So yeah, what you see here, I cannot really show it, point at it, right? But the first red line shows what's in the first line on the slide. So the probability of t given d times the probability of d. Okay. And since we know this correspondence, so we're basically doing the same thing, but a bit from a different angle, 2 ways of solving it. We know the probability of the first world, and we know the probability of the other worlds where t is true, right? So this is the marginalization again. We sum up the worlds where t is true. Well, no, sorry. What was this part? Yeah, I'm sorry. Yeah, it's the marginalization is the sum of the worlds. I was confused with d and t, right? So we know t, we want to look at t being true, and we sum over all the worlds that have t true, we fix that, but then we marginalize over the disease, which is disease is true and disease is false, and we sum up those two probabilities and get to the same result. Empty faces. Maybe questions to this. So the normal way, how I normally do this is with this variant, right? It's a bit more intuitive with the formulas we got. But yeah, you can reason over worlds and sum them up, which is basically doing exactly the same thing. Right? What we do in this step, summing up these two worlds, is this step. Okay, it's the same thing, just visualized differently. So the world 1 and world 3, this is world 1, this is world 3. Right? And then we have the world 1, which is the one we're looking at, right? T true, D true, divided by the other two worlds. So we have actually plenty of time left. Let's see, so you can think of some questions you have. Let me summarize the lecture. All right. So we've seen what is a belief and what are events or statements. Then we have seen what happens to our beliefs when we get some evidence. So when we observe certain things and we know they are true, how does this change our belief and probability in things? And then we talked about independence, right? When two events are independent, or when they are independent, even giving more evidence. And we said independence and conditionally independent. And we also discussed more properties that are then useful to use in Bayesian networks, like the chain rule and the Bayes theorem, which, by the way, the Bayes theorem is useful in a lot of settings, not just in this. Yeah, that's that for today. Any questions, remarks? Yeah?
Question on slide 22.
All right, let me see. No worries. Yeah. Now, oh, stop.
Data is 0.
Yes.
I was having trouble.
its meaning?
It basically means that for an event that is impossible, any other event will be independent. So if the probability of beta is 0, this event cannot happen, but then it can also not have any influence on any other event.
The probability is not 0, but still it's independent.
Yeah, that's the usual case. Okay, so maybe what the whole statement means, right? That the left part holds when they are independent, with the exception of beta being, the probability of beta being 0.
The definition of alpha given beta involve dividing by the probability of beta.
Yeah.
Then surely you can't give the alternate case that the probability of beta equals 0, because then
Yeah, so
alternative, surely it should be, it can't equal that.
so what it means is if beta is 0, you cannot say express this, right? Because as you say, you have to divide by 0. But then you just say, okay, if beta is 0, you don't take this fraction that leads to this statement, but then you just say they are independent. So you avoid this dividing by 0.
Yeah, if one's impossible, then it doesn't depend.
Yeah. There is no point in doing the update, basically, if the world is impossible. Any other questions? All right. Then, yeah, I would leave it to that, and see you tomorrow.
Any time for it.